Hello, our project is FRGB Instruments, or Frequency-Based RGB Lights. It was sponsored by Professor Leinecker. Frequency-based RGB lights are customizable light strips that change color and brightness according to noise frequency. Our goal for this project is to have it fully customizable via software application and easily attachable to any instrument. The specifications that we have set up for this project is to have a minimum SNR value of the ADC of 25 decibels, to have a minimum refresh speed of the code of 5 iterations per second, to have fully customizable colors for each note, and for it to be relatively portable inside of a certain weight and size. The expected outcome of our project is to have a microphone set up to Raspberry Pi 4. The microphone will read in the sound frequencies being created by an instrument, which the Pi will convert to a numerical value and assign it an RGB value. That RGB value will be outputted from the Pi to an LED strip attached to the instrument to create a light show. The screen connected to the Pi is used to display the GUI that the user will interact with to customize the lights. The entire system is currently powered by a wall outlet. The hardware components for the project are a DC-DC converter to regulate the voltage, an analog to digital converter to convert the microphone signal to digital, and a Raspberry Pi to control the system and run the lights.
There are different types of DC to DC converters, but the one used in our practice is the switch DC to DC converter. The reason for us using the switch DC to DC converter is to be able to make the device portable with a small voltage source, meaning less batteries in the future versions, and to add the use of a switch to turn the device on and off from the power supply. Issues at practice. Connection with the wall mount and to the microcontroller was the main issue, being that the microcontroller only accepted a power supply that utilizes a USB-C type. In our design for the DC to DC converter, there was no ports. At first, it was thought to just connect the wires directly to the port, but however, we are now designing a future iteration with ports on the DC to DC PCB to actually install directly into the microcontroller. This is the analog to digital converter. This PCB design hasn't been ordered yet due to testing issues. However, it can be ordered within days of finalization of the testing. The significant components include a crystal oscillator to act as a clock, a digital filter with the I2C to communicate with the Pi, an integrator, a difference amplifier, and a comparator.
This is our ADC converter. In our design, we are using a comparator, a D flip-flop crystal oscillator clock, a switch, and a unity buffer op amp, as well as this outer circuit, which we are testing because of issues of our integrator and our difference amplifier not working well in our second order filter or our first order filter. The components are acting erratically, so we are getting extreme oscillations as our outputs, as well as our op amps not behaving well. We think it's the bypass or decoupling for the capacitors, so we are switching them out and buying new parts, hopefully before the final demonstration, and we'll be getting this all sorted out, as well as finishing our testing for the main ADC. All these components as well have been functioning perfect. It's just this filter is not working that well. We'll be getting this done all within deadline.
During the testing stages for the ADC, the team ran into various issues such as the design and components aspect. For the design issues, it was desired to construct a second order delta sigma modulator ADC. However, with consistent errors in the testing for the filters, having two might pose a bigger issue than just having one. The team will continue the current design and overcome the issues in the next 1 to 2 weeks. The current biggest issue is that the components, specifically the op amps that make up the integrator and difference amplifier, being faulty, not working in any applications we tried. New op amps have been ordered and will be arriving within 1 to 2 weeks. Hopefully, the new ones will also work and it will solve the issue right away. However, the issues we were facing with the op amps were that the op amps were too big of a frequency inside, causing extreme oscillations within the op amp because our input signal was too small, causing the output signal to be way more distorted than desired. As well, in the beginning testing stages, the op amps were tested without a bypass capacitor to the power supply, which also could have been the extreme source of oscillation to our output signal. We are trying to get this solved within 1 to 2 weeks and have received help from outside sources to get this done.
Here we have our Raspberry Pi, which has been fed power through a wall outlet over USB-C. The Raspberry Pi is then connected to an LCD touchscreen. The LCD touchscreen can take user input through touch. The Raspberry Pi is also connected to the LEDs through the GPIO pins here. These LEDs are currently connected to a guitar. We also have our microphone connected to the Raspberry Pi via USB. The USB is terminated into an XLR connector. The XLR connector is then fed through a preamp, and the preamp is then connected to the microphone via XLR. In these next slides, we're going to go over our software implementation with our graphical user interface using Tinker, our Python code, the console output from the code, as well as a small software demo. We used a Python library called Tinker to help create our user interface. Tinker has many assets to help create user interfaces such as buttons, labels, frames, and panels. As you can see, we have a small demo set up right here. The first panel has two elements, a welcome message and a continue button. The user can interact with this continue button to start the program. The next panel has a message and a button as well as a label that updates. In the next slide, we'll show this label that updates in real time. In the future, we'll have a third panel to let the user select different themes for the LEDs. In this slide, we have an example of our real-time updating label. This label, when the program is running, updates in real time and shows the user of the program the individual note that is being played. This can be useful for many things. First off, you can use this to, say, tune your instrument. Second off, it gives a visual feedback for the user to make sure that the program is actually running if there's no output from the LEDs. In the future, we will incorporate color coordination as well with the note output that corresponds with what's happening with the LEDs.
The following images represent one of the classes in our Python program that we had written to test our product throughout the development phase of our project. Since we are working with another computer science team, our program is a simplified version of what they have created despite us having written our respective programs in different languages. You can see in the image on the left that we utilized the PyAudio and NeoPixel Python libraries. These libraries allowed us to read in the sound frequencies and control the output of the lights respectively. We then read the data, conduct a few calculations, and then, as seen in the image on the right, assign each frequency to a specific musical note. The following two images represent our most recent test of the Python code shown in the previous slide. The image on the left shows the microphone reading the same note over an extended period of time, while the image on the right represents the microphone reading multiple different notes over a short period of time. You can see how the output tells us the frequency of the noise emitted along with the musical note it corresponds to. In future tests, it will also tell us the volume of the noise being read in by the microphone. Moving forward, we plan to add a setting for perfect fifth notes, which is basically a mix of the colors of two notes merged together, a fadeaway effect as the volume decreases, and fully customizable color themes in our GUI for the user to play with.